So how do we handle inductors in a circuit? Well, just like we started off with resistors in a circuit, we're going to look at inductors in a series circuit. When inductors are connected in series, the total inductance, L sub T, is the sum of the individual inductances. And so we can see that mathematically here, L sub T is equal to L1 plus L2 plus L3, etc., etc. Notice the calculation of total inductance in series is analogous to the calculations of total resistance in series. So it becomes very, very easy. Inductors in series, we handle them just like resistors in series. So let's look at a simple example. Determine the total inductance for each of the series connections. Okay, so we've got two problems here. A, we see a 1, 2, 1.5, and 5 Henry inductor, and in B, a 5 millihenry, 2 millihenry, 10 millihenry, and 1000 microhenry. Okay, so on that one, we're going to have to be careful that we have to change our units here to make it fit into the millihenry scheme. So for the first one, simply add 1, 2, 1.5, 5, and we get 9.5 henries of inductance. For the second one, we have to handle the 1000 microhenry. They made it simple on us. We removed the 3 zeros and we're back to millihenries. So 5, 2, 10, and 1 millihenries gives us a total of 18 millihenries of inductance. So pretty simple. Parallel. So for parallel inductors, we have to look at it like that of parallel resistors. So again, they've made it pretty easy on us. When inductors are connected in parallel, the total inductance is less than the smallest inductance. The general formula states that the reciprocal of the total inductance is equal to the sum of the reciprocals of the individual inductances. So we calculate it again just like we do with resistors in parallel. Okay, so we sum all of the reciprocals in the denominator, flip it one more time, and we get our total inductance. So just like resistors in parallel, we have inductors in parallel. Another simple example. We've got a 10, a 5, and a 2 millihenry inductor in parallel. So we apply the general expression, L total for the three inductors, 1 over L1, 1 over L2, 1 over L3, summed in the denominator. When we sum them, take the inverse, we get 1.25, 1.25 millihenry. So it's just like our resistors. That should be pretty simple and not a difficult task for you at this point in your electronic technician career. So looking at inductors in DC circuits, we need to start looking at how we handle inductors in a circuit that might include other components like resistors to start with. Energy is stored in the electromagnetic field of an inductor when it is connected to a DC voltage source. The buildup of current through the inductor occurs in a predictable manner, which is dependent on something called the time constant of the circuit. The time constant is determined by the inductance and the resistor in the circuit. So what we're going to do is look at how these two components act and work together in a circuit. So again, simply starting off in a series circuit, when there is a constant direct current in an inductor, there is no induced voltage. There is, however, a voltage drop due to the winding resistance of the coil. Again, it may be minuscule, but nonetheless, there is a winding resistance. The inductance itself appears as a short to DC. Energy is stored in the electromagnetic field according to the formula previously stated. Energy is equal to 1/2 L current squared. The only energy conversion to heat occurs in that winding resistance. Power is equal to I squared R sub W. This condition then is illustrated in this little diagram here. So we can see as the fields start to collapse and the current stops flowing, we end up with dissipation greatly in the resistance in the winding and energy stored in the inductor itself. So what we need to do next then is look at something called the time constant, in this case for an RL circuit. We've seen it for the RC circuit in the previous videos, so now it's time to take a look at how we handle the time constant for an RL circuit.